Hi, I'm Professor Rand at the University of Michigan. I'm the director of the Murray Center for Dynamic Magneto-Optics here. And we're here today to see a demonstration of the EinsteinDeHaasEffect. This is an interesting effect from the turn of the previous century, in which Einstein attempted to show that what we now call spin, which involves molecular scale currents, can be converted to external motion. That is, the internal angular momentum, which is there but invisible normally in all materials, can be converted to a real macroscopic motion of the material. And I'd like to introduce Monica Wood, who's going to tell us how this works. Monica, what do we got here? What are we looking at?
All right, so we have a function generator that we will send the signal through a power amplifier, which we will port into a 500-turn solenoid here. And we have in the center of the solenoid a solid...
Sorry to interrupt. This produces a magnetic field that
Correct.
Oscillates up and down? Okay.
Correct. And suspended in the center of this solenoid is a solid half-inch steel rod, which is then suspended from two steel wires that if you were to torque it, will have some resonant frequency because of the suspension. And we will set our function generator at that resonant frequency, and as the signal goes into the solenoid, it will produce that magnetic field, which will then torque on the rod and cause it to rotate.
So is it right to call this a torsional pendulum, and the frequency you're talking about may or may not be resonant for the natural motion of the pendulum?
Absolutely. This is definitely a torsion pendulum, and the frequency that we will oscillate it at is indeed the resonant frequency of the pendulum itself. And so for this specific rod, our resonant frequency is 1.8 hertz. And so if I go ahead and start the output there, we will turn up our amplifier, which is increasing the amplitude. And in a moment, we will see resonance happen.
So this is a weak effect, and we're waiting for it to build up.
Absolutely.
Even though we're on resonance, it takes some time. Oh, there we go. So that's what happens on resonance. Is there a way to show off resonance behavior here?
Absolutely. So I'm going to turn down the amplifier. We will stop the motion of the torsion pendulum. It takes a fair amount of time to die down. We will then turn our function generator off resonance. So we're going to go to 2.5 hertz, so not far. And then I will go ahead and turn up the amplitude once again. There you have it.
So the idea is that this time we're off resonance and do not expect any motion to build up. Even though the basic effect is still present, we don't have the benefit of resonance. Okay, very good. So no angular motion, although there's a little motion back and forth because we're not quite centered. So the reason we're interested in the EinsteinDeHaasEffect has to do with a discovery recently made by the center in which light is shown to do something similar to what you've seen here. But in the case of light, is a two-step interaction in which light not only provides the internal microscopic currents or response, but also produces the magnetic torque responsible for large magnetic effects in the end. And here you've seen a demonstration that the effect of magnetic torque can cause macroscopic motion. That's part of the optical effect that we've been studying. So the EinsteinDeHaasEffect has a new relevance a century or so after it was introduced by Einstein and DeHaas in the 1900s.